Dave. Let me sort out my camera. There we are. Somebody's been asking me recently, no, actually not me, they were asking you about removing the air out of a H10 and H5. Remind us what those apparatus are and the process of removing the air. Why it's important to remove the air, because some people know what they are and some people won't.
Yeah, well, the H5, we're looking at Bernoulli's theorem using a Venturi and manometers. The H10 is flow measurement, so it does what the H5 does. But we also look at different methods for calculating coefficient of discharge. So like the H5, it has a Venturi, clear perspex arrangement, sudden contraction, sudden expansion, with pressure tappings all along that section. But it also has an orifice, which is another method for calculating flow rate or discharge. And it has a rotometer. So it does a bit more than the H5, but they still share. They are very similar in appearance, but they can still suffer, if not tended to, some problems with having trapped air bubbles. Okay, a little bit of air didn't hurt anybody. Okay, but with the H10 and H5, if you've got large pockets of air, then you are going to get some strange spurious results. So it's a good idea to get as much air out of the system as possible. So my technique is to fully close the valves on the H5 and H10, open fully your hydraulic bench, and that could be your H1D digital or H1F digital flow bench. So open up fully the delivery valve on your hydraulic bench, then slowly open your valve, your control valve on the experiment until water starts to flow through. You'll see a lot of bubbles starting to get dislodged. You'll see water start to rise in your manometers. Okay, that's where most of the air is going to disappear from. Eventually, the water levels will rise to such a point in those manometers that you have to open the Schrader valve on the top glass manifold. Okay, that's basically a tire valve that you'll be familiar with. Once you've done that, you can then exit the air out of the glass manifold, and eventually you'll see little or no air flowing around the circuit. But that adds another challenge, because you need to get those water levels down to a sensible level. So we do that by getting the bike pump or the bicycle pump off the side of the unit, screwing it into the Schrader valve and giving it 4 or 5 short, sharp pumps. You'll then see the water levels lower down to a sensible level, let's say 300 millimeters, and then you're ready to start the experiment. So that's how I get the air out, and I've just copied the procedure in the manual for that. So that's the method for removing excess air out of the circuit.
Brilliant.
Okay.
Thank you, Dave. You might notice I've shown that up on the screen here so that people can see that as we're talking through that. Now we have got a question. We've got a question, which is, when working with the structures software without the hardware, are there manuals supplied with software experiments?
Yeah. With the STR 2000, which is the ADA, you do get a dedicated manual with detailed notes on how to conduct the experiment, which you can then compare to your hardware experiment and also your virtual experiment, which is what you get with the STR 2000.
Right.
You get all the supporting material needed to do all 3 methods of experiment.
Okay, and then this can stand alone, can't it, as well?
Yeah, the virtual experiments, once you've got the STR 2000, you can then conduct all 19 of the TecQuipment structures experiments virtually. So you do not need all the hardware, you just need the STR 2000 software, which is what you see there. So you do shear force, bending moment, bridges, suspension bridge, 2 simply supported beams, all sorts of different civil engineering work.
Fantastic. Well, I must admit, the person who asked that question is quite impressed, and the response is, "You're the man, Dave."
If he needs
So
any further support or assistance, he can come to me directly or through the customer care inbox or through Dion. It'll end up with me eventually, I hope.
it will. It will. We'll make it happen.
Splendid.
Great. Thank you for that, Dave. The next thing I want to talk about is strain readings on, let's look at this. I'm going to show it on this screen, if I can see.
I can see what you're doing there, Dion. You're quite literate on the computer.
Yes.
You may have a future in marketing.
Oh, well, you know what? Should think carefully about my career.
Yeah.
Structures
I
range
recognise
now.
this. Yeah, I recognise
Redundant
this.
truss. It's quite nice when we can have it on the screen like this, isn't it?
It
Rather
is.
than
It's
talking
working
blindly on Instagram. Great. So you can see the redundant truss. Can you explain? I'll zoom in the picture. How do we set it up, and how do we take the strain readings on this one?
Well, let's assume our customer has fitted the truss to the frame. That's a very simple technique. Just follow the manual. There are dimensions in the manual that show the recommended positions of those supports on the left-hand vertical frame member. Connectivity wise, it's impossible to get wrong. So the load cell can only connect to the STR1. There's no way of defeating that. And equally, all the individual strains on those members are numbered. So they go to their respective sockets on that digital strain meter, which is at the forefront of that picture. Okay. So we've got that member now in its relaxed state. So nothing's applied. We can't just go straight in and do the experiment. We have to preload that frame to remove any sticking and friction. In the manual, we refer to it as a stiction, which is a cross between sticking and friction. Okay?
Is that a word, or is that we've made that word up? It
I don't think
sounds like
you'll
a
find that
made-up
in the
word.
Oxford Dictionary, but you'll find it in all of our structures manuals.
Stiction, great.
Stiction, okay. So we've got that STR8A load cell on the right-hand side, and it's at the bottom right of the structures frame, the structures arrangement. We need to apply a preload to that structures experiment. So we'll quickly zero the STR1A force meter, okay? Then we'll apply a downward load of 100 newtons to that frame. And when you get to 100 newtons, we then zero the STR8A load cell. So that's giving us a starting point to do the experiment. So although it's zero, there is actually 100 newtons already applied, but because we've zeroed the force meter, that now becomes irrelevant. We can forget that now because we're starting at zero. But we need to do the same on the strain meter, okay? So you can see where all those strain wires are connecting in. Well, we can't see on this picture, but adjacent to those sockets, there are individual small blue potentiometers that allow us to zero the individual strains from those members, okay? And when we've done that, you can rotate a small pot through each of those members and zero the strain readings accordingly. Then you're ready to do the experiment. Only then are you actually ready to use the experiment in anger, if you like.
Okay. And does that work in the same theory with the pin jointed frameworks experiment?
Absolutely. And also for the STR5 as well, which is the bending stress in a beam experiment. In fact, any experiment that has strain, then you need to do that same procedure. You need to apply a preload.
Great. Well, I just thought I'd throw something up here. Some people have particular challenges sometimes assembling the roof trusses experiment. I wanted to highlight that we've got quite a nice video from Matt Fellows who explains how to assemble that. So a bit of a tip if you are looking at how to put that one together and you're following the manual. I'd recommend watching this video at the same time. It makes it so much easier.
Yeah, it does take a little bit of concentration. I tend to lock myself away for 10 minutes in a broom cupboard and build this, because you need to concentrate on exactly the correct angles and the lengths of the members as well. So it just takes a bit of concentration.
Okay, good.
Once you've done it once, it's like riding a bike.
Right. Brilliant. There we go. Look at that. It's all done. That
There
shows
you
how
go.
quickly and easily it can be done. And now it's
It
going to
can
pop
be
it
done
on
quickly,
the
yeah.
frame.
Yeah.
Okay, let's moving back to this now. Next question, Dave, is about VDAS on the AF 1300 subsonic wind tunnel.
Yeah.
This does have VDAS capability, doesn't it?
It does. It does.
How does this all work, and how do you actually take all your readings, and what are the opportunities and limitations as well?
Well, you've mentioned before, Dion, the main benefits of VDAS is it's much quicker and easier to get readings. Less errors can occur. But for the VDAS to be fully effective on the wind tunnel, the customer will need to have certain essential accessories. Okay, not optional, they are essential. So they will need to have differential pressure gauges, digital differential pressure gauges.
Okay.
They in turn measure the pressures inside the working section. So the upstream or right hand digital pressure display is used to calculate the wind speed velocity in the wind tunnel. That gets fed back to VDAS, and VDAS itself does the maths. It does the calculations, because VDAS knows the pressure. You've already inputted the ambient atmospheric temperature and ambient atmospheric pressure. So just with the pressures and those temperatures and conditions, the VDAS itself can calculate the wind speed, which is super easy and makes the whole experimental procedure much quicker. Okay. They can also order a downstream digital pitot-static tube. That is basically a emitter vernier, but it connects to VDAS, and then you can actually see the position of the pitot tube in millimeters on the VDAS screen, on your computer screen. And because you can enlarge those boxes, it means you can actually do the tests and take readings from a distance as well. Okay. And with the time recording on VDAS, you can start the experiment. It will collect data every half a second up to 2.5 seconds until you've finished. Then you can disconnect VDAS, remove any of the data sets that you don't want. Then you can dump it into Excel, into Microsoft Excel, and do your manipulation away from the lab. So that's the beauty of VDAS. It's quick. It's much less error-free than the human touch, if you like, and it's convenient as well.
Brilliant. Good. Thanks for the explanation on that, Dave.
That's okay. I can see then that in that video we can see the 3-component balance, and also we offer the 2-component balance that is also VDAS compatible, so it will send back the lift and drag readings in newtons and the pitching moment in newton meters as well. So that again allows for a much more greater value to the whole setup.
Great, thank you for the clarity on that. For those just joining us on this YouTube live Q&A, this is an opportunity to ask your questions, whether it's a student and you're struggling with a piece of theory, or whether you're an academic, you're thinking about how can you set up a piece of apparatus, how can you prepare it for decommissioning over the summer period. Do put your comments, your questions in the comment box below, and I will put those to Digital Dave. Now, Dave, I would like to talk about this particular piece of apparatus now, the benchtop heat exchanger.
I know it well.
Good. Okay. So these, if we skip to it, these different individual module experiments that sit on the front, you can see the one with the yellow pipes at the moment. How easy are they to switch over? Is that something that you're going to need a load of training on, or we can
no. designed especially for ease of transfer. So
Right.
we've got 4 types of heat exchanger: jacketed vessel and stirrer. We've got the shell and tube, concentric tube, and flat plate. They all share the same area on the plate. So the plate's held on by 4 knurled screws. You can just about see the screw holes there in the corners. Then the customer will need to disconnect the hot water pipes and the cold water pipes. Because these are quick release sealing connectors, you'll get a few drops of water, but because they self-seal, you will not have a problem with flooding the bench, okay? But it's still good practice to turn down the hot and cold needle valves, just so no water is building up in those coloured pipes, okay? So when you've swapped out the old heat exchanger, place the new one on the surface, attached with the 4 screws, connect your hot and water pipes according to what configuration. So parallel flow or concentric flow. They go in different positions, okay? So luckily we've built in a mimic diagram on the plate so you can easily follow the connectivity easily enough. It's a very simple process, Dion, less than 2 minutes per swap over, so minimizing any downtime in the lab. There we go.
Thank you very much for that. Okay, so the next question is, on the SM1000, this is our big tensile tester. Yeah. Let's pull it up. So, oh, look, there's all kinds of SM1000s in YouTube. Let's put in TecQuipment SM1000 universal testing machine. On this particular piece of apparatus, I'm just looking at the comments now. How do I change from doing a tensile test to a beam test?
Okay, well that's going to take a little bit longer than it would be to change a heat exchanger, okay? So the tensile test being a destructive test, you need to remove the specimen clamps. There's a jaw, if you like, at the top and the bottom of the SM1000 working area. Once they're clear, with the help of 2 other people, they need to lift the beam through that working section, and then with a very sturdy hexagon bolt that is supplied, the beam support is clamped to the underside of the upper part of the working section. I can't point it out here, but it becomes quite clear once they see it. Once that beam support is fitted, you then get the beam and you fit it to the supports on the beam support. Then they fetch the digital vernier gauge that's measuring the overall extension of the beam. So it's a mid-toroid gauge. The magnetic keep sticks itself to the beam because the beam's magnetic. Then we set to 0 on that gauge. We set the load meter to 0. Then we apply the force via the hand pump, and we are measuring load against extension. That makes up the axes, load and extension. Because it's a non-destructive test, we do not test the beam past its elastic limit. So it's not a plastic test. We are just looking at that linear straight line graph of load against extension.
So no destruction, no breaking of any beams are required in that particular experiment.
No, unlike the tensile specimens that you're seeing there, we are not going past the yield point on that graph.
What indicates that you should stop when you're doing that experiment?
Well, and that's a good question, because you get the beauty of the hand pump. Okay, you actually get feedback through your arm. Okay, so as you are loading up that beam, so you will see the load increase and you will see the deflection increase. But the moment you start to see the load leveling off, that's when you stop, because you know that you've reached that yield point or the limit of proportionality. So you must then stop the test. Do not go any further, because
Okay.
you are then entering into the plastic region of the experiment, and that beam will be bent and it will be unusable for future use.
Okay. Dave's top tip of the day: when it stops, when it's not flexing
Yeah,
anymore, just stop. Do
and
no more
honestly,
before you cause damage.
you can get enough data points within that elastic region not to come anywhere near the yield point.
Okay.
You
Right.
can get maybe 100 points on your graph.
Well, okay.
Or however quickly you can click your mouse, or if you're doing a timed recording, you can do it every half a second and say, let's stop after 20 seconds. That will ensure that we don't go into the yield point and beyond.
Brilliant. Great. Thank you for that.
Okay.
For those who've joined us more recently on YouTube, or if you're watching this on demand, those on demand can still post the comments in the comment box below, and we'll send you some text replies. If you are watching live in the moment, please put your comments in the box below, or I will ask those to Digital Dave, and he will give you the answer. Right, okay, let me see what my questions are that I have here.
Do you think, Dion, we should use this opportunity just to talk about if any of our customers have to decommission their equipment over this period of time?
Absolutely.
I don't know.
I mean, if you're fortunate enough to be able to get into your labs, to be able to sort them out and decommission them, maybe Dave, you could take us through some very popular pieces of equipment. I will pull up some videos at the same time as you're doing that, so that people can see them.
I think that's a good idea, because this applies for the most part to our fluid mechanics range, Dion. So we don't want to be leaving any water in our experiments or in the reservoir tanks. So we'll start with the fluid mechanics. So if you've got any of our modular fluid power products, that's MFPs, or if you've got an H47, H83, H400, they all have integral reservoirs. Okay, so in the picture there you can see, let me just see what Dion's pulling up there.
Which one do you want me to pull up then, Dave? MFP?
Just go to MFP 101, the top one.
Okay. Oh, okay.
Yeah,
okay.
MFP 100, MFP 101. So that's got a big black reservoir of water. I think it holds about 100 and maybe about 150 litres. But going back to what I said, all those experiments I just mentioned, they all have drain valves underneath them. So just introduce a hose pipe or a drain pipe and get that water not only out of the tank, but also out of the pipe work and also the centrifugal pumps. Gravity will do the rest. All the water will naturally flow out into the drain. Okay. I'm sure a lot of our customers with their fluid mechanics will be running hydraulic benches. So H1F, H1Ds, they all have drain taps underneath. Again, get that water out. And just, if you have access, use a hose pipe to swish around, get any tide marks, any dirt, any dust out of those tanks into the drain. Still on fluid mechanics, if you've got any flumes or flow channels, if you've got the latest FC range of products or the older H12, H23s, drain wherever possible. Okay, the H12 has a built-in reservoir tank. It also has a drain plug. Get the water out. H23 is lined on a hydraulic bench. So I've already covered the hydraulic benches. Get the water out and flush with clean water wherever possible. Okay, and then we can move on to the actual experiments themselves. The H5, H10, H30, H40, H7, H16, H34, H408, H215, H13, H9, and so on and so on. Get the water out of those experiments as well, using clean water wherever possible. Okay. There's more. If you have H405, TE86. Then we move on to the hydrology, the H312, H313, H314, and even the H31. Empty these of water, okay? Now, you might be tempted to use compressed air just to clear out any excess drops of water. Do not use compressed air. This could have a catastrophic effect on any seals, any pressure points, any glassware, manifolds, etc. on your experiment. That will be game over then for your experiments. So please just use the atmosphere and the drain to get water out. Do not use compressed air, okay?
Okay, do not use compressed air.
Yeah, do not.
And cause damage.
We've already spoken about heat exchangers this morning, about how easy it is to swap them. These, by their very nature of the quick sealing connectors, leave water in them, okay? But you can defeat the quick sealing connectors. So you simply get your pen and you stick the pen inside the connector, and you just apply pressure to the spring-loaded ferrule inside, and that opens up that connector, and then you can drain the heat exchanger of water. You'll always be left with a little bit of moisture in there. It's inevitable, and just by the nature, they will start to fog up a little bit with condensation. This is normal. Do not be worried about that, okay?
Okay.
We can move on then to thermodynamics. If your lab has a TD200, this is a water-driven dynamometer, but fortunately this drains itself naturally. But also we need to get any of the fuel out of the fuel lines, because there's nothing worse than dirty, contaminated fuel. Over time, fuel perishes. It turns into a horrible color, and eventually, if you've got diesel, will turn into a syrup, into a horrible oil.
So if you're leaving it over the summer, say for 3 or 4 months, is that long enough for the fuel to go bad? Right.
Yeah, especially in
how
hot
long
countries.
Could you leave it for? Could you leave it over Easter, for example?
You could leave it over
2
Easter
weeks?
for sure. You can leave it over the Christmas period, up to a month. I would leave petrol or gasoline or diesel in those fuel lines. It's like if I left my car for a month, I'd always want to run it just to make sure nothing gets stuck or seized or oiled up, okay? It's just good practice, and technicians will know this. They should know this, okay? I
would say that's the top tip for those who are self-isolated as well.
Yes.
Not leave your car on the road or on the drive, and
no.
Every now and again go out and give it a blast.
Just move it and get those brakes working. Handbrakes can seal. Even overnight, if you look at your discs on your car, you'll see oxidation. You'll see corrosion starting just after one evening of rain overnight. So that's important. But we diverged a little bit there, Dion.
Sorry.
Okay.
Back to where you were.
Back to where we were with thermodynamics. If you've got a steam plant, a TD1050, absolutely imperative that you drain the boiler of water. So you've got a drain valve underneath the tank, get it into the drain and get it flushed out, okay? This is the most important tip for the day, more important than anything I've said so far. You must introduce oil into the TD1050 engine cylinders. So we'll undo the bleed screws and we'll just either syringe in or pour in gently some oil. It can be engine oil, it can be any kind of oil, it could be steam oil that comes supplied with the TD1050. Get oil into those cylinders, get those cylinders lined with oil. So just turn the flywheel on the engine so the pistons go up and down and they draw oil not only onto the walls of the cylinders but onto the top of the piston. Remember, it's a cast iron piston and it's a cast iron engine. When you have two similar materials, they tend to want to bond together. They can't do that if we get oil in there. So pour oil in there until it overflows out of the drain valve, okay? My voice is starting to go.
Oh, quick, get the water,
I'm taking
Dave.
a drink. All right, so you think it just applies to fluid mechanics? It doesn't. If you have structures or material testing, ensure all your load cells are left in their relaxed state. Take off the load on your structures, take off the load on your beams, and also your specimens. Make sure there are no loads applied, because over time we get creepage. Load cells can become a little bit deformed over time. So it's very good practice to undo your STR8As, for example, which is what you see on the top member of that portal apparatus. Okay. And then finally, well, we also have reservoirs on our control engineering range. Okay. So empty these reservoirs, flush them with clean water to prevent any ink or dye from leaving stain marks on your equipment. And then finally, airflow, aerodynamics. They also have manometers. So if you've been using dye, or coloured ink, get those manometers flushed with clean water to prevent any tide marks or any drain marks being left over this period of time. Okay. And the same for fluid mechanics manometers as well. Just flush with water. Okay.
Okay.
So that covers pretty much everything within our range that could be vulnerable if left over a period of time, Dion.
Right. Okay.
Right.
Okay. Right. Fair enough. Good
That's
stuff.
a lot to take. That's a lot of information to take in. But if our viewers have individual questions about their individual equipments, then we can tackle those offline through our customer care inbox.
Or, for that matter, join us later at 4 o'clock on YouTube
or come back again.
Yeah, because we will be back again. We're doing these live on Instagram, live on YouTube. Wednesday is the live stream Q&A day. So note down your questions throughout the week and join Dave and I during those sessions. I should mention a few other things quickly before we leave today. We've introduced a new resource for people who are doing remote learning. I'm going to try and pull up the web page. Learning. That I think many people who are stuck at home, it would be good if I could spell remote right. Remote learning, report learning. Okay. Content, remote learning support. Okay, so we have a whole load of resources that are available for people. We've got the Wednesday Q&A, so if you're working and studying from home, you've got questions, then do join Dave and I for those. We've got a community on the YouTube channel, so if you're on our YouTube right now or you're watching it on demand, go and look at the communities tab. It's the fourth one along the top. Post your questions in there, ask polls, look at the videos that we're sharing. These are general industry videos. And talking of videos, we've created a useful guide of informative videos that you can find on YouTube. They're not Dave and I or other colleagues or even people at universities using TecQuipment products. It's interesting stuff, whether it might be a comparison between what's the difference between centrifugal and centripetal. Interesting external videos that you may find will help your understanding of engineering principles, help academics teach their students in a more engaging way rather than just the presentations that they're watching online. So do check out the link for that on this particular web page. The URL is techquipment.com/remote-learning-support. We'll put the link in the box after we've closed this live stream down for you to follow. We're also releasing lots of new student experiment videos. We already have some of those on YouTube. We'll be releasing more of those. So again, if you're wanting to see how a certain piece of equipment works, then do check out some of those experiment videos where students are showing them using them. Sometimes you can see results as well. If you're trying to fill knowledge gaps, reconnect yourself with practical elements of it, of engineering, then they're a great source. For academics in particular, we've also got communities on Facebook and LinkedIn where you can go and ask your questions and share ideas. And do reach out to us if you need specific help. You'd like Dave's assistance with addressing a group of students, maybe privately rather than on this public forum. That may well be something that we can assist you with. So you can put a comment below or email marketing@techquipment.com or customercare@techquipment.com. We will follow that up with you. Have I missed anything, Dave?
No, I think you've covered everything. But just like what you said, just reach out to us. You know, I'm contactable. Email, cell phone, any questions, product related, any difficulties, use us. That's what we're here for. Yeah,
we may not be in our headquarters. We're both in our home offices, but we are busy people, and we're really looking at how can we support you guys in the best way. So do make sure that you let us know how we might be able to do that and make the most of the resources that we're making available for you.
Yeah.
If you're watching this on demand, don't forget to like and subscribe to the TecQuipment YouTube channel so you don't miss any more of our videos or live streams coming up in the future. You might want to check out some of the playlists and videos that we already have uploaded.
Splendid.
So I would say that's pretty much it from us today, Dave. Well, for this morning, let's put it that way. We will be back.
We'll be back.
We'll be back. We'll be back at 4 p.m. British summertime. If you just put in, work out what time that means for you. We will be back then for another live Q&A, and we will be back next Wednesday. If today doesn't work for you, return next Wednesday and ask your questions then. So thank you very much.
Yeah, thank you everyone. Keep safe, everyone.
If you stay there, Dave, I will say goodbye to everybody and we will be good. Thank you and goodbye.